Have you ever looked at a giant spreadsheet full of data and wondered, how on earth does this become a smart predictive model? Well, in this explainer, we're going to break that whole complex process down into a clear 7-step blueprint that you can use for pretty much any project. Alright, so here they are. These 7 steps are the core life cycle for basically every successful machine learning project out there. We're going to walk through each one, taking you all the way from that first spark of an idea to a real working solution. Think of this as our roadmap. And to make it even easier to follow, we've bundled those 7 steps into 4 main phases. This is going to be our guide for the journey, taking us from the blueprint all the way to the finished product. So let's start at the very beginning with the foundation. And I can't stress this enough. Even the most powerful cutting-edge model on the planet is completely useless if it's solving the wrong problem or if it's built on a shaky foundation of bad data. Getting this part right is absolutely crucial. The very first thing you have to do is define the problem. What are we actually trying to achieve here? Are we trying to predict a number, like the price of a house? Well, that's what we call a regression problem. Or are we trying to sort things into buckets, like figuring out if an email is spam or not spam? That's a classification problem. Knowing which path you're on right from the start changes everything. Okay, so we have our goal. Now we need to get to know our most important asset, the data. This exploration phase is, well, it's like being a detective. You're not building anything just yet. You're putting on your investigator hat, looking for clues, searching for patterns, and trying to spot any hidden problems. And visualizations are your best friend here. You might plot a histogram of house prices and suddenly see that, wait a minute, a bunch of them are capped right at $500,000. That's weird. Or you could use a scatter matrix and instantly see a really strong connection between how much people earn and the value of their homes. This is where you really start to build an intuition for what you're working with. All right, let's head into the construction zone. Believe it or not, this is where a data scientist spends most of their time, taking all those raw materials we just investigated and actually shaping them into something a model can understand and learn from. And that brings us to maybe the single most important rule in all of machine learning. You've probably heard it before. Garbage in, garbage out. It's a cliche for a reason. The quality of the data you feed your model will directly, 100%, determine the quality of its results. You just can't build a great model on messy, unreliable data. It's impossible. So preparing the data involves a few key things. First, cleaning. We have to deal with missing values so they don't break our model. Then there's feature engineering, which is kind of cool. It's where we create new, more helpful features. For example, maybe combining number of bedrooms and number of bathrooms into one total rooms feature is more powerful. After that, we have to scale our numbers so they're all in a similar range. And finally, we encode any text-based categories into numbers that the algorithm can actually work with. Now we get to the really cool part, the training. We take our squeaky clean data and feed it to a learning algorithm. At its heart, training is really just a process of trial and error. The model makes a prediction, it checks to see how wrong it was, that's the error, and then it tweaks its internal settings a little bit to try and be less wrong next time. It does this over and over and over, thousands of times, trying to get that error as close to zero as possible. And you've got a whole toolkit of algorithms to choose from. Each one has its own strengths and weaknesses. You might start with something simple and interpretable, like a linear regression or a decision tree. Or you might jump to a more powerful approach, like a random forest or gradient boosting, which are called ensemble methods, because they cleverly combine hundreds of little models to make one super prediction. So we've trained a model. We're done, right? Well, not so fast. How do we actually know if it's any good? Is it ready for the real world? This next phase is all about quality control, rigorous testing, and fine-tuning. The absolute golden rule here is that you must evaluate your model on data it has never, ever seen before. So what we do is we split our data up. We use the biggest chunk, the training set, to teach the model. We use a smaller validation set to tune it, and then we keep one final untouched test set locked away until the very end to get a final honest grade on how well it performs. So how do we grade it? Well, accuracy, just counting how many I got right, is a good start, but it can be really misleading. Think about a spam filter. We might care a lot about precision, which asks, of all the emails the model called spam, how many actually were spam? Or we might care more about recall. Of all the real spam out there, how many did our model manage to catch? These metrics give us a much richer picture of what's really going on. This quote from Aurélien Geron's book points to one of the biggest traps in machine learning. Your model might get a perfect A+ on the data it trained on, but then completely fail when it sees new data. We call this overfitting. You can think of it like a student who just memorizes the answers for one specific practice test, but hasn't actually learned the subject. So how do we fight this? How do we get our model to generalize better? We do it through something called hyperparameter tuning. These aren't the parameters the model learns on its own. These are the high-level settings, the control knobs that we set before the training even begins. Finding the perfect combination of these settings is the key to building a truly robust model. Now, finding these perfect settings can feel like searching for a needle in a haystack, so we use automated methods to help us. A grid search will literally try every single possible combination you give it. A random search is a bit more efficient and just tries random combinations. Both of them use a technique called cross-validation to make sure the performance gains they find are real and not just some lucky fluke. All right, we've reached the final phase. We've built a model, we've tested it, we've tuned it. Now it's time for the launch. Putting our model into a real system and realizing that, you know what, the work is never really over. And that's because building a model isn't a straight line with a finish line at the end. It's a circle. It's a continuous loop. We deploy the model, but then we have to monitor it. Is it still working well a month later, a year later? We take what we learned from monitoring it, we analyze its mistakes, and we use that knowledge to go back and build an even better version. This whole ongoing process of monitoring, retraining, and redeploying, it actually has a name. It's called MLOps, which stands for Machine Learning Operations. It's the entire field dedicated not just to building a model, but to running it reliably in the real world so it keeps providing value over the long haul. Which brings us to our final and maybe most important takeaway. The world is constantly changing. New data comes in, people's behaviors change, and new patterns emerge. Because of this, a machine learning model isn't some static artifact you build once and forget about. It's a living system. And just like any living system, it needs continuous care and feeding to stay sharp and effective.